Applications ranging from bosonic string theory, black holes, superstring theory, to M theory. These beautiful concepts play significant roles in the above-mentioned fields. Let's try to have a few introductory ideas on Q series and the theta functions. An important task is to first understand a few notations which we will be using. This product form is a famous one, and Q is called the base. Once the base becomes obvious, we can ignore the Q. For n equals 0, we have the result as 1. For n equals infinity, we will represent the product in the following way, where mod of Q is less than 1. Now, what is a Q series? It's basically a series which contains coefficients which are of the form AQN. But in multiple instances, we might not encounter summands of this form. Instead, we might have the theta function. Ramanujan's general theta function is defined by the following, where mod of AB is less than 1. We have three special cases which, when defined by Ramanujan's notation, looks like the following: the phi of Q, psi of Q, and f of minus Q. Now, let's have a look on some fundamental theorems on Q series and theta functions. The first one is the Q analog of the binomial theorem. Let's keep its proof for some future videos and just have an overview for now. Now, why is it called an analog of the binomial theorem? Let's take the limit of Q approaching 1. The limit can be solved using L'Hopital's rule, and we will have this expression. Now, when we take the sum, we note that the right hand side finally turns out to be 1 minus z to the power of minus a. This is the generalized binomial theorem. Two important corollaries will follow, credits to Euler, and I would recommend keeping a note of these two corollaries as we will be using them in future videos. The next thing that we have is an identity of great importance, Jacobi's triple product identity, which says the following. In Ramanujan's notation, it looks like this. We will try to prove this now. Recall this corollary, where mod of z is less than infinity. We will replace q by q square and z by minus zq. We will have the following. This expression is important, so let's keep a copy of it. Then we will have this, and then this. You can try to figure out how we got this last part from the previous as an exercise. The hint is writing the expression in product form and shifting some terms. Now, you might have noticed that I changed the expression or the limit from n equals 0 to n equals minus infinity. We can do this as we note that this expression is 0 if n is negative. This can be seen if we write it in the product form. When k will be equal to minus n minus 1, this expression inside the product will become 0, making the entire product 0. Now observe this expression. We will now apply the identity here. On applying, we get the following. Exchanging summations, as these are finite sums, and a bit of rearrangements, a bit more with mod q by z less than 1. Let's write n plus r as m. Now recall this corollary. We can apply it to this expression, which will give us this expression, and we will finally have our required identity.